So recall very quickly that last time what we had seen. Oops, and now my stylus is not working. Okay, give me a second. So okay, good. So we'll continue and continue with some properties of entropy before going on to a lower bound. So recall very quickly that entropy was this measure of uncertainty in a random variable. And the two important properties that we had seen of entropy was, well, a couple of important properties, that h of x is always greater than or equal to 0, less than or equal to log of size of support of x. Okay. What else? We had seen that if you take n random variables, we had seen it for 2 and 3, that h of x1 to xn is less than or equal to h of less than or equal to the sum. And we had defined the notion of conditional entropy, and we had seen the chain rule, which also said that h of x1 to xn is equal to h of x1 plus h of x2 given x1 plus so on. And the standard notation used in information theory is generally you have xi for a fixed I, and x less than I denotes all the variables, the random variables x1 to xi minus 1 just concatenated together. Okay, so a small maybe clarification and slightly silly, but important to note that when I write h of xy of this form, it doesn't mean the product variable xy. It means the concatenated variable x comma y. So okay, the chain rule does apply for this way, and we had also seen this nice property that which follows from subadditivity and chain rule of entropy, that h of say x given y conditioned on any random variable, the entropy of a given random variable can only decrease compared to its original, or the uncertainty can only decrease. I mean, the random variable y will not harm. At max, it might help somewhat in reducing our uncertainty about x. Okay, so we'll need a couple of properties today to go towards the index function lower bound. And instead of proving it at that point when we reach it, these are intuitive enough properties that I feel are worthwhile stating before. So the first one, and this is like quite obvious, is that h of x is the uncertainty is x is greater than the uncertainty of any function that is completely determined by x. Well, this is kind of obvious intuitively because it's a deterministic function f, right? And therefore, any function can only decrease the uncertainty if at all. For instance, if I have x over the uniform domain from 1 to n, uniformly distributed, then the entropy of x is something like log n. Now, suppose I put a function on it that reduces it to a 0, 1 variable that just thresholds it at a certain point. It's the indicator function of x greater than or equal to some t. Okay, in this case, you're making a function of this. And what is h of y? Well, h of y is at most 2. So the entropy has decreased. So this is the sense in which we are talking about functions decreasing entropy. Okay, of course, if the function y depends upon x in some way, we can get some more non-trivial bounds about this. Okay, in particular, because it's uniform, the entropy is at most 2, but you can get a tighter bound because it is 0 with probability something like t over n and 1 with probability 1 minus t over n. So in fact, this entropy of y can be exactly determined, and it's less than entropy of x. Okay, so the proof of this is quite an easy application of just the chain rule with some logic. So the idea is that suppose I give you x, then f of x has got 0 entropy, right? Because it's a deterministic function, there's no uncertainty in f given x. This is just a fact. But we know that by chain rule, this is equal to h of x comma f of x minus h of x. So this means did I miss something? Okay, sorry. This is equal to 0. I don't need to transpose anything. So you just get that h of x is equal to h of x comma f of x, and this is greater than equal to h of f of x. Okay, because this is also equal to, by chain rule, h of f of x. So basically, we're using chain rule in two different ways. Right, and this thing is non-negative. So yeah, this is quite an intuitive property. The second one that we'll use is slightly more non-trivial, but still makes intuitive sense, which is called Fano's inequality. And this is the kind of thing that we'll really be working with quite a bit. Okay. So let us say that you have two random variables, x and y, that are of course jointly distributed. In particular, we're going to use y as, let me say x and y are bits. And we are planning to use y as a predictor for x. Okay, so intuitively what we mean is, suppose I given y, then using y, somehow I'm going to try to guess what x was. Okay, this is equivalent. If you see in the communication complexity setting, Alice will send a message to Bob, and Bob, using that message, should try to gain some information about what x is. Okay, so in a similar way, think of y as the message being passed to Bob. Okay, so the idea behind showing this, maybe I can give this as an exercise for later, but it's worthwhile giving the idea behind this. So what we have is x. So y is my thing, and I'm going to use as a predictor. So basically, you're going to do some function on y, right? And use it to predict what x is. So this is the general idea. And if y is a good enough predictor for x, that is, there's some function f such that the probability of error. So from f of y, I output some estimate of x called x hat. And the probability that x hat not equal to x, that is the probability of error. Notice that we are just working with bits for now, and this is just the version that we need. The probability of error, and this is, say, P of E. So this is a definition. I've not yet stated the inequality. Then Fanos inequality says that it should be the case that if y can be used to predict x with small error probability, then the entropy reduction or the new entropy of x given y should be actually small. Let me just write it. Okay, so I'll just write this as p and I'll put this as p. It's a probability of error. Okay, so notice that this is the binary entropy function. And h of x, as I noted last time, is nothing but x log x. Okay, and let's see that this peaks when x equal to half. Okay, so this is the entropy function. The entropy of x given y is at most this. So maybe I will give an outline of how this proof goes. The idea is to introduce a new random variable e for the error.
Sir?
Yeah.
Sir, can you explain that like notation of Fanos inequality, like this part, if?
Okay, so what I mean over here is that y is being used as a predictor for x. So in particular, what is happening, think of it as a process that gets y and tries to recover x from it, okay, not knowing x in advance. So in that case, what you'll do, you'll apply some function of y on the received input y, and that would give you some estimate x hat. Okay, now that x hat estimate that you get of x might be equal to x or may not be equal to x. So suppose y is such a variable that you can estimate x using y with probability of error being at most p.
Sir, can you give some example for this?
Sure. So let us take the simplest example. Suppose x and y are the same. Okay. So if x and y are the same, then what will happen? Well, y is an exact predictor for x. Okay, so the probability is equal to 0 of this error. You can just put f of y equal to y. Okay. On the other hand, suppose you use something slightly different. Okay, so for instance, suppose x is uniform like before in 1 to n. Okay, and you know, y is a variable that just tells you whether x is even or odd. So what is the probability of error? Now, y is revealing some information about x, but it is quite small. So it kind of reduces the domain to be uniform on n over 2 numbers, right? And then from that, the best you can do for guessing x is like you can guess x just with probability correctly 1 over 1 over n over 2. Right? So it does reduce, but the probability of error can at most probability of error is 1 over 1 minus 1 over n over 2. Okay, which is quite large, but yeah, that's how it goes. But it is giving you some information, so it is reducing the amount of error that you incur on predicting x. Okay.
So sir, as of here, given x, so y will tell whether x is even or odd, right?
Right. So using that, you're not going to be able to predict x very well, but the error probability does reduce because after that you can do a random guess of some sort, and you'll be correct with some probability.
So sir, like y will tell whether x is even or not, but not predict the exact value, like out of those n by 2 possibilities of x, it can't get to one value, exact value, right?
Exactly, yeah. So it does reduce your error in probability, but it does not reduce it by too much. Okay, so this example X is not really a bit, um, but the inequality, Fanos inequality generalizes to when X and Y are not bits. Now, the most general case when X and Y are bits are basically when you have X and this is equal to Y with probability P, not equal to Y with probability 1 minus. In which case, again, you can do a similar analysis. Now, the analysis that I'll do here actually applies to the general case when X and Y are not necessarily bits, but we'll use the case only when X and Y are.
So, sir, like Fanos inequality says like entropy, like information known, like given y. So how much information that uh, x information that we get is upper bounded by like error probability
Right,
entropy.
right.
Okay.
Right, because see, if the error is very large, then correspondingly, that means Y is not conveying or Y is not causing any reduction in the uncertainty of X. So H of X given Y should also be large. Okay. And if X is predicting Y with very good probability, in fact, look at the boundary case when they're exactly equal, then the entropy of X given Y is equal to 0, which is again the probability of.
Yes, the probability will be low. Error probability.
Yeah, the error probability is 0 in the extreme case. So,
Okay.
yeah. So this is quite an intuitive lemma. So what I will do is I'll just introduce the technique behind it, and there's no real need to go into the proof of it currently. It's just the application of the chain rule. So introduce an error variable E that says that, well, okay, maybe first thing I will show is that before introducing the error variable, I'll just say that the uncertainty given Y is surely less than X given X hat. Okay, where X hat is the predictor that I'm using Y, whatever it might be some function of what Y is. And this is because, X hat is a function of Y. And so whatever the information that Y is helping you with, if you kind of reduce it down into a function of that, then the function of Y can only kind of reduce the uncertainty less. And now what we'll do is bound this. The idea is to introduce a random variable E, which is 1 if error occurs, 0 if no error. Okay. And now under this, we'll just use the chain rule in two ways. You look at this quantity, and then on one side, you can expand it as h of x given. So at this point, it's just, possibly hat. And the other side, so notice that there are two possible expansions of using the chain rule of entropy. This is something that conditioned on a variable is what was your exercise in the previous lecture. But even conditioned on a variable, you can use the chain rule just as it is. And now I've put x as the primary variable at the first term. Here I can put e as the first term. Okay, and now what we'll do is we'll rearrange this in order to get the result. Um, Oops, sorry. This is equality. What am I doing? It's a chain rule. Yeah. Okay, so now I can rearrange. I was afraid the inequalities are going in the other side, but notice that the h of error given x comma x hat is equal to 0 because given both x and x hat, you know exactly whether there's an error or not. Okay. So this is equal to 0. Okay, and now all this remains is to bound both of this. And notice that over here, um, h of e given x hat is going to be at most the probability of an error. Plus now if you expand this, you'll find that the other term is going to go to 0. So leave this as an exercise. Because yeah, it's kind of obvious. You know the error variable and you know x hat, so you know what x is. So this is a binary random variable. Okay, so this intuitive version is what this quite a nice thing if you can generalize it to bigger domains. Okay, so keep these two in mind, and now we'll return back to our initial problem, a communication problem, which is the index function. So what is the one-way communication? What is the indexing problem? Alice is given a string X, which is a bit string. Bob is given an index I. Okay, and the aim is to find out is for Bob to find out what the ith bit of Alice's input is. Now, you can see very easily that if Bob starts first, then all he needs to do is send across. This is an asymmetric problem. Alice's inputs are n bit long. Bob's input is just log n bits long. And therefore, if Bob sends across his input completely, then it's log n bits. Okay, because you just send these log n bits across, Alice returns back the bit, they're done. On the other hand, what happens if Alice is constrained to start and only one message is allowed? So that's why it's called one way. So these are the constraints. Can send a single message to Bob. There's exactly one message M, which is going across. And now depending on this, Alice has to answer X. So clearly this seems hard. Even with error, it looks like you cannot do very well, right? Basically, Bob needs to be able to predict every bit of Alice using this message because Alice doesn't really know which bit to send across. And therefore, what we'll show is omega in lower bound of this. So I'll allow a delta error and maybe the error I will just rephrase to be half minus delta. Okay, so this is the main theorem that we're going to show. So notice how this really nicely sets up in terms of the information complexity or the information terms we've discussed. Bob is basically using M, the message M, as a predictor for Alice's X. right? Because he should basically know every coordinate of X because you don't know what input Bob is using. And therefore, if M is a predictor for X, right, then M should be large enough so that it can reduce the entropy down. So we'll formalize this in a moment. So what we'll do, as usual, is go to distributional. And we'll show that for a certain distribution mu over the inputs to Alice and Bob, this is greater than or equal to omega delta squared. So what is the distribution you're going to use for inputs to Alice and Bob? Well, Alice is going to get, so this is the distribution that we set up so we can do, like we choose it cleverly. In this case, it's not, it's the normal one that you would expect. Alice gets a uniformly random string, bit string in 0, 1 raised to n. And Bob gets a uniformly random index. So UAR means uniformly at random, in case you're not used to this notation yet. Let's me who's messing up the notation. Should write it. Yeah. So I is drawn from n, x is drawn from 0 and raised to n. So this is my distribution. And we'll start off by saying that suppose there's a deterministic protocol for this. Okay. And so that means Alice looks at a string, sends a single message across. Of course, this message might depend upon what X she gets. Okay, so I'm going to denote the message as pi. Okay, or protocol or transcript. Yeah. So this is the transcript. Because it's just that whole transcript is just a single message from Alice to Bob. You can just call it a message. So recall that now, because there's a distribution over X, pi is a function of X. And is wholly deterministic and and is random and is therefore random because X is itself uniformly at randomly drawn. So what we're going to look at is the entropy of the transcript pi. So if you look at h of pi, so this is the starting point of all information theoretic proofs. You look at the entropy of the transcript. And what we'll show, because of our previous result, that h of pi is at most bounded by the log mod of the support of pi. Okay, so this is nothing but if pi takes values over this domain, then of course you need to encode it, as we know. Yeah, by at least log of the support. So this is by our inequality. Now this thing is what? Well, this is greater than equal to, well, this is a trivial thing. In fact, this is an equality because pi is a function of X, and as you had seen, h of pi given x is actually equal to 0. Given x, you know what pi is because it's a deterministic protocol. But we'll just leave this in because what I'm going to do is I'm going to re-expand this and write it instead as h of x minus h of x given pi. So why is this justified? Well, it's just a chain rule being applied. Both of these sides are equal. So you have h of x and pi taken together is h of x plus h of pi given x. And it's also equal to h of pi plus h of x given pi. Right. So if I just rearrange this, I get that h of pi minus h of pi given x is equal to h of x minus h of x given pi. Okay. So this step is clear. This is a key step, and that will occur in all information theoretic proofs that you will see. Okay, so what do we do next? Well, now we use all the tools that we can. What is h of x? Well, x is a uniformly random bit string, right, from 0, 1 to the n. So h of x is indeed equal to n. It's entropy of n bit long string. It has got n bits in it. Minus, what is h of x given pi? Well, x is just a collection of n bits x1 to xn. And this we know we can do using the chain rule, right? So I'll just put this in bracket, h of x2 given pi x1 plus 1, h of xn given pi and x less than. And now when we have this, we are going to use the fact that conditioning only reduces the entropy. Right? So each of these terms here is less than equal to okay, so what I'm doing is I'm basically reducing the conditioning and therefore increasing the entropy of each of these terms. So now I'll write that this is greater than equal to because it occurs with a negative time, negative sign over here. Okay, so notice how this is nicely played out using the algebra of chain rule over here. What you have reduced it is that you've reduced it to the fact that what is the entropy of xi, a single bit xi, given pi. And this is actually something that we should know because what we know sorry, yeah, so we know that, pi is a good predictor for every xi. Right, irrespective of what I is. And if you have going by Fan's inequality, should be less than the probability of error, which looks like delta. So There's a catch in this, which I'll come to in a moment, but intuitively, h of xi given pi should be less than equal to h of delta. And therefore, the inequality here leads to h of delta. Sorry, this is half minus delta. That was the error. Okay, so this is the general idea, but yeah, there is some kind of issue in this. So the issue is that you have to be a little careful when I apply Fano's inequality over here. Okay? And the reason is that the error when you're looking at distributional complexity is not pointwise error. It is error over the entire distribution. So each of this is not in the worst case having error half minus delta, right? Rather, it is having some error for every combination of, say, I and pi, and the overall average over x and I is going to be equal to delta. So there is a small thing that needs to be tackled. But with convexity, it's going to finally reduce down to this same expression. So for a given message and a given index, let the probability of error be some delta I pi. Okay, so for this thing, there is a probability of error. And what we'll do is just use, maybe this, I'll write it as half minus delta. But what we know is that the average, of course, is going to be half minus delta. Where the expectation is over the input distribution. That is I and X, basically. Or rather, delta is equal to equivalent. So the only small thing that we need to do is to figure out how to apply Fano's inequality to each and then sum it up.
So
Okay, so
why will the error be an expectation over I as well?
Well, okay, so it doesn't really matter what I said because you're saying that it's just a random expectation over pi. No, see, so there are two types of randomness. So for every I, there might be a different error for a given message.
The I is the ith bit in the
I is the index that Bob receives over here. And
okay.
Yeah, and that is uniformly randomly chosen from n. So he might make more error on some indices under the distribution than others, but on average, the error should be at most delta.
Okay, then it's fine.
Okay. Okay, so maybe we'll just write this out a bit more carefully. So what we'll do is bound every h of xi given phi, but is equal to, well, for this fixed thing, we have error at most delta im. So I should have introduced, I used half minus everywhere. And therefore, what we'll just do is we take the expectation over this. Is less than equal to half minus delta. And this thing is the expectation over II is uniformly randomly drawn. And therefore, this is just the sum. And x and I, if you remember, was independent, right? So this is just I equal to 1 to n of 1 over n, expected value over what were the input distribution. Okay, but the averaged over the input distribution for a fixed I, this is nothing but yeah, so this thing actually should be over pi. Yeah, small point, but it's not, yeah, nothing great to talk about. So the expected value of the error over this is exactly the kind of term that occurs right above. And therefore, this is 1 over n. 1 to 1. Half minus delta. Oh, so yeah, so this is where I missed the point. I'm sorry. So this is less than equal to, because it's a predictor, it's h of this quantity. That's why I was thinking why this is so trivial. So this is at most, so Fano's inequality states this. And because Fano's inequality states that this is h of this, then what I need to do is basically take the expectation of h of half minus delta I. Okay, and now what we'll use is we'll use Jensen's inequality to take the expectation inside. If you recall, h of x was, the binary entropy was concave. So this is less than equal to h of, sorry, this is still a binary entropy. It's my h of half minus delta. Okay, so yeah, sorry about the slight mess up, but the idea is basically this, that that we are going to use convexity to just reduce, to average over the errors in every individual coordinate, because you cannot predict a worst case point error of half minus delta. Okay, so this should kind of make it, I hope, at least clear about the way that we are using information theory. Recall that at the starting, I will just recap this part because there's a lot of algebra happening in between. We said that suppose there's a C-bit protocol. Then what do we have? Well, C is log mod of the support of pi. And this we said is greater than h of pi, which is greater than equal. And somehow magically we are able to transfer this into terms that involve the prediction of every xi given pi, which is exactly our indexing function prediction as needed. And this we shown, this was n, this was half minus delta. Okay, after this h of half minus delta times n. Now the only thing that remains, recall that I had shown that I told that we'll show that it is omega delta squared n. That's just a bit of algebra at this point, because this is h of half minus delta. Now, what it's kind of worthwhile to do this algebra once because it relates to another quantity that I'll introduce soon, the divergence. So, well, I'll just split this as half and half, but we'll see that in a moment. I'll just write this as half minus delta okay. So why am I writing it like this? For the simple reason that this is a well-known quantity that most of us would have seen before. Notice that you get half minus delta minus log. The divisor is what I've added in at every point. Of course, there's a negative sign. You can check that that just works as it is. So when I add in this divisor, this, if you notice, is nothing but something called the KL divergence between the uniform distribution, or rather, first I should write this. P is a distribution on 0, 1, which is 1 with probability, doesn't really matter. Half plus, it doesn't matter whether I put 1 or 0 here. And the uniform distribution is 1, or rather, Q is the uniform distribution. Oh, sorry, this is 1 and 0. So, in case you have not heard about the KL divergence before, it is just a measure of distance between two distributions that is actually asymmetric. And we have estimates on what DKL can be for different values. The idea of introducing this here is just to kind of introduce a new inequality that is very, very helpful, which is called Pinsker. So all of this is to estimate, what this constant is over here, 1 minus h of half minus delta. What does Pinsker's inequality state? It states that between any two distributions, so the two distributions PQ should be on the same domain. I have something called the KL divergence, which I hope you're familiar. If not, I'll define it soon. Is greater than actually, I'll write it this way. This. Okay, so what is this inequality stating? It's just a simple bound on something that is complicated and involves logs to something that is just a L1 norm. So this is the L1 norm between the vectors P and Q. If you view the distribution as vectors, in this case, they have support 2. And this is the scale divergence big quantity. So I introduced Pinsker because it's quite useful in information theory to move from such an expression to something like the one norm of P and Q. Okay. The one norm of P and Q between P and Q has got more intuitive explanations that we can use. But in any case, let us finish this. What is the one norm between P and Q, where it is this distribution, right? It is just delta, because half minus delta minus half, half plus delta minus half. So this looks like 2 delta. So this implies all the way above. Look at, we had started from this chain of inequalities and led it to this, and we have estimated this last quantity to be at least n. So there are quite a few tools introduced along the way. If you have any questions about any of them, please ask. I'll just summarize by zooming outward. So once we got down to this point, n times 1 minus half h of 1 minus delta, we wanted to estimate this quantity. So for some reason, I expressed it as a distance between two distributions where the distance function is not, I could not call it a distance, because it's not really symmetric between P and Q, where P is this half minus delta, half plus delta bit probability, and Q is the uniform distribution. And then we use another inequality to relate this to the one norm, which gave us a direct handle on what the communication complexity is in terms of delta. Okay, we could have left it in terms of this h of half minus delta, but it's not really significant. It doesn't give an idea because the entropy function is so complicated in its dependence on delta. It doesn't immediately give us an idea what the dependence on delta is. Questions? Please ask. I don't have much else that I plan to cover. I'll introduce some other terms, but this is more or less the kind of meat of what I wanted to cover for today. What did we introduce? We introduced the KL divergence between two distributions P and Q. They are on the same domain. Is this quantity divided by Q of X? And then what we introduced again was Pinsker. Okay, so yeah, so I hope the general proof outline is clear. If there are any questions, please ask me. I'll pause for a moment here, have some water, and we'll get back to our next section. Okay, so now that you have got to this part, we have shown a concrete lower bound on indexing. So in fact, the power of information theory is not just to show these one-round lower bounds, but it is for something more, which is actually related to disjointness. And for that, we need to define something called as mutual information. So I've been talking about, all of this entropy being the uncertainty in a variable, or equivalently the information contained in a single variable, right? And the only thing to relate to variables was the conditional entropy. So whereas the conditional entropy actually said what is the decrease, or like what is the entropy remaining in X once I reveal to you what Y is, a measure of what is the common information between two variables is the mutual information. Maybe, yeah, essentially X, Y, A, B. So this is the common information that is contained between X and Y. Okay, so recall for intuition that h of X given Y was equal to, I have to define this quantity, but recall that entropy remaining in X when Y is revealed. Whereas this is how much information is actually common to X, and therefore I'm going to define this using a term. Okay. So this is a definition. And which you can rearrange. You also get that it is equal to h of X. Because this thing, h of xy minus h of y, as we had seen last time, is equal to h of x given y. And this, you can also get it as h of y given x. It's a bunch of manipulations to give these identities, but the following inaccurate kind of picture or intuition that is often used is, suppose this denotes h of x, then denote h of y, then this is often, this intersection is called I of x. I don't like this picture because it leads to a lot of wrong concepts, but it's something that might help when you're starting. Okay, so I hope this is at least slightly intuitively clear. One thing that you will notice is that the mutual information between x and y is always non-negative. Why is that? Because if you notice both of these formulae, it is h of x minus h of x conditioned on y, and the second term is always smaller than the first. The other thing to note is that what happens when x, y are independent? Then the mutual information between x and y is actually equal to 0 because there's no common information that is contained across x and y. Formally, it's because h of x given y is equal to h of x. In fact, it's an if and only if. And finally, what happens if a equal to b? That the x equal to y. In this case, h of x given y is 0, and therefore everything that is there in X is like common to Y, and therefore this is H of X also equal to H of Y. Now, if you go back to our indexing proof, let me just scroll up. So if you look at this very start, what we had here in the first line is exactly the mutual information between the message and X. Okay, and we just rearrange that into its second form over here. So it makes intuitive sense that we are trying to characterize how much information is contained between the transcript and the protocol, the transcript and the input X. Okay, any questions about mutual information yet? So we'll look at a couple more properties, and yeah, maybe one simple example like last time, which will help to understand this. Okay, so let's take three variables. How can we define mutual information on three variables? It's kind of not, there's no natural extension of 2 to 3 like there was for entropy, because you're looking at the common information between X and Y. It turns out that if you try to naturally generalize something like this to three variables, it does not work, does not have obvious or intuitive properties. But suppose I have three random variables. So this, the kind of quantities that we can define though are, you take AB as a single variable and look at the information with C. So notice that unlike in entropy, it's important to put this colon separator that shows what you're taking the mutual information. Or you can also have similarly I of A, C, and B. I mean, there's nothing. Now the last two are the same. Okay, so given this, let us try to kind of figure out, maybe for the simple example that we'd also seen last time, if A, B, C are bits, and they are drawn uniformly at random, conditioned on, say, the parity is even. So the question is, we had seen what the entropy of these groups of random variables are. Makes sense to look at what the mutual information is. Okay, so what is, first of all, maybe I'll start off with this. What is the mutual information between just A and B? So it's uniformly drawn conditioned on this equal to 0. So like last time, you'll recall that any two of them are pairwise independent. The random variables are pairwise independent. So any two of them are independent taken at a time. So the mutual information between A and B is equal to the mutual information between B and C is equal to 0. However, if you add in the third variable into this mix, what happens? In this case, well, I'm going to expand out like usual. So according to the rule of mutual information, it is h of first variable minus h of the first variable given the second variable, or I can also do it the other way around. Which of these is slightly easier to evaluate? Well, the second expression is slightly easier to evaluate. simply because I know that h of c is equal to 1. And given A and B, C is completely determined because their XOR has to be 0. So once I give you A and B, C is known. So this entropy of C given AB is equal to 0. There's no uncertainty left. So this is equal to 1. If you went to evaluate this, then of course you would have to compute h of AB is equal to 2. But the entropy of AB given C, as we had seen last time, is, well, you're determining up to the parity of A and B. And therefore, after that, you have one more bit of information. So 2 minus 1 or 1 minus 0 both lead to the mutual information of AB given C. So you might ask, what happens? Does similar properties as subadditivity also hold for mutual information? Well, it turns out no. And given this very example, one can try to figure out. So I of AB given C, if I wanted to kind of write out a rule of subadditivity, I would try to compare this. So notice there are two variables here. So I'll try to do subadditivity over them. Okay, but you have just noticed that this is not less than equal to this, which is what subadditive would imply. For above example, we had that this is equal to 1 and each of this is 0. So subadditivity is not always satisfied. Here's an example. Superadditivity is also like, so maybe the other side holds because it holds for this example. Turns out no. So you need to think a bit more to get this example. But the basic idea is that, you know, if a variable determines two variables, do I need this? You can also increase. Maybe there's a simpler example. Yeah, so even this set does not hold. Don't have immediate example in mind. I thought this would work, but does not seem to. Maybe. So I'm going to try find an example for this. Okay. Okay, so yeah, so it looks like, oh, in fact, if you have them to be equal, okay, so right. So if A, B, and C are completely equal, then in that case, I of A given C is equal to 1. This is equal to 1. And this is also equal to 1 again. Okay, A, B, C are uniformly random bit, just that they are the same copy of the bit drawn uniformly at random. Okay, so this is less than equal to neither of these holds. So it depends on the situation that we need to work with what we do. Okay. So subadditivity, superadditivity, neither are satisfied, but it does satisfy a chain rule. Which it's kind of what you would expect if you just write out chain rules syntactically. This is equal to Well, you could take the first variable plus, notice that for chain rule, you require a sort of definition of conditioning, but I will take it as write it down and then define it. This is the conditional mutual information. But again, whenever in information theory you have conditioned on something, it just means the expected value over the distribution of this random variable that is conditioned on the mutual information of everything which is conditional. So take the distribution of A and C, joint distribution of A and C conditioned on B being some fixed value. Okay. So this requires a proof, but the proof is quite easy. It's just you expand everything out in terms of entropy that we already know, and this will just follow. Yeah, so you can write everything in entropy conditioned on B. And okay, so I've introduced this new notion of mutual information that does not, unfortunately, I don't think we'll immediately have time to see a lower bound that utilizes this, but I want to kind of give you the context or idea of what helps with proving lower bounds. Sorry. So recall that in the one-way communication setting, we could just think of, say, the message from Alice to Bob and characterize everything using the entropy, which in some way, if you notice, was the entropy of the random transcript was greater than equal to the mutual information between X and the transcript. Okay, and then this is what we tried to bound. So the information cost, in some sense, was characterized by this. And what we knew was that the communication complexity is greater than equal to this information cost, and the cost gave us a bound, a good way to kind of get the bound on what we need. It turns out that you can define this more in general for general protocols. So we'll need a notion of the information cost of a protocol. Okay. Notice that because it is now a like you can have back and forth between Alice and Bob in a general setting, just the mutual information between Alice's input and the transcript is often not sufficient to characterize or get a lower bound on the communication complexity. So a natural notion, there are two natural notions that one can define as part of the information cost of a protocol. Again, I'm going to assume that X, Y are the inputs to Alice, and there's a distribution mu over them. Okay. In fact, more generally, Alice and Bob can use shared randomness, private or public, in order to actually, after getting the inputs to communicate or do things, that's the most general setting that one can work with over here. But I'll kind of ignore that point for today's remaining 10 minutes. So we define the external information cost. As what? Well, the external information cost is defined as intuitively, it is how much an external observer learns about Alice and Bob's input if they have access to just the protocol. So how much information, just like we had between just X and Y, here's a natural extension. How much does the transcript give an external viewer information about both X and Y together? The other notion is the internal information cost. Okay, and this is defined as the sum of the information that Alice learns and Bob learns about the protocol, about the other person's inputs given the transcript alone. So it is basically, so if you look from Alice's point of view, what does she have? She has X already, and she wants to learn about Y from the transcript. So this is what Alice learns. And this is what Bob learns. Okay. A really nice theorem, which unfortunately will not get to prove today, is the following. That the internal information cost of any protocol is greater than, is less than equal to the external information cost of a protocol, which is at most the communication complexity. Yeah, which is the length of the transcript of pi. Yeah. Now, the point is one has to be a bit careful here. This, as you would expect, because you're working at information, this is the expected number of bits exchanged. Okay, it's not the kind of worst case. Yeah. The expected under mu of what is it? The proof of this is not very difficult, but one thing to realize is like whenever you're dealing with information, often there's a notion of rounds because you want to look at how much every round reveals information. So you can break this down round by round of the protocol and prove it. Okay. So I'll not prove it today. We are almost out of time. So instead, I'll keep it for the time when we revisit information theory to use these kind of terms and techniques to prove other lower bounds. Okay. So we'll see where to do it. Either we'll do it in disjointness or we'll do it for gap hamming or some other such problem. So the real power of information theory, or the most common use that has turned out, is possibly not to show these single functions, but to show low bounds for functions like disjointness, where actually it is like an AND of many inputs. So it's like a copy of many inputs. So you have two sets, xi and yi. And what you're looking at is that there should not be any coordinate where it is all zeros, right? So yeah. So there should not be any coordinate in which both are ones. So that is like an OR of ANDs, the negation. So if you have multiple copies of the same function that you want to combine in some way and prove a communication lower bound for that function f, then this kind of information theory works really well. That is the most, that is where this really shines. Anything else that I wanted to say? So of course, we have defined this information cost. One last point is that we have defined this information cost for both internal, external, whatever. But even you can have a protocol that is very long in terms of worst case number of bits, but has very low information cost. So for instance, if you take the very simple, coming back to the AND, if you take say AND function, so Alice has a single bit, Bob has a single bit, and they want to compute what the AND of xi and yi is. So in the models that you have seen, or the cost that you have seen until now, this is trivial. I mean, you need at least one bit. And so Alice sends across her bit, Bob knows, that's it, we're done. But one needs to assess what is the information cost of this protocol. And you'll see that one can get, so it's like Alice needs to send Bob, then Bob knows the answer, send back. So it looks like two. But you can have more information efficient protocols that actually are very long in the worst case. So it's actually non-trivial to find out what is the information complexity of AND. Or what is the best case? Okay, so what is the best? What kind of protocol will give you or leak the least information about this while allowing them to compute their answers up to probability? Yeah. So that's so yeah, all of these are very non-trivial questions. Some of them are still open. So we might come back to information theory maybe next lecture or after 2 or 3 lectures, depending on what we look to cover next. So I'll stop here for now. If you have any questions, please ask.